Good day, class. Today, we're going to cover Chapter 10, or at least 10.1 and 10.2 for Introduction to Statistics at College of the Sequoias. We're on our lockdown for COVID-19, but the show must go on, and there's some good content here. This is the chapter that we start exploring hypothesis testing. And this is what all of statistics, what we're almost always trying to work with. So hypothesis testing. 10.1 gives us an introduction to the idea. And 10.2, I'll go over the actual test. Okay. So let's say you and I play a game. We flip a quarter, and every time it lands on heads, you pay me $1. And since I'm feeling generous, every time it lands on tails, I pay you $2. I think I'm a better flipper than you. I can flip better. And I get to be the one that flips. So I flip the first coin, and the first coin lands heads. And I pick the coin up again, and I flip it again, and it lands heads again. And you're getting frustrated. You've already had to give me $2. I flip it again, and my third quarter is heads. Or the third flip is heads. And now you're like, I don't know, this is starting to sound shady. You flip it again, heads. A fifth flip gets heads, and a sixth flip gets heads. We flip a coin 6 times. And they all end up on heads. You owe me $6. Now, what kind of assumptions do we make here? Our main assumption is the probability of the flip equaling heads equaled the probability of getting tails, 0.5. Okay, that's the assumption we make. Now, if that's the case, what's the probability of this happening? What is the probability of getting 6 heads in a row? Well, let's go back to probability. That means the first one equals heads, and the second one equals heads, and third equals heads, fourth, fifth, and sixth equals heads. And these were independent, and they're mutually exclusive outcomes. All that good stuff says we can turn these additions into the probability the first equals heads, times the probability of the second equals heads. And we keep doing the multiplication until we have probability of sixth equaling heads. Each one of these is 1/2. This is 1/2 to the sixth power. Should be 1/64. Which is approximately 0.015625. So, and you've seen this in the problems that they like to give in math lab. If we conducted this experiment (1,000) times, hell, let's make it 10,000. 10,000 times, only 156 times will we see 6 heads. In a row. What if you'd said, okay, at what point you're going, maybe he's got a fixed coin, they exist. I actually, when I was your guys' age, in my early 20s, I had a coin that had 2 heads. Did I have that here? You don't know. You really don't know. What if you, but at some point you're going, okay, this is starting to sound shady. Maybe the coin's weighted. Maybe one side's heavier than the other, so it lands downwards more often. 5 tosses. We would have had 1/2 to the 5th power. 1/32 is still very low, or about 3%. And remember, less than 5% makes it unusual. So this was unusual. We flip it 6 times. 6 times it was heads. And 6 times you gave me a buck. You gotta, what are the possible reasons this could have happened? Option A, although unusual, you were just unlucky. Option B, the game was rigged. Either the coin was weighted or at double heads. It just ends up being how it is. Which one is it though? You don't know. But the fact that it was unusual, this is where hypothesis testing leads. Hypothesis testing we made an assumption of equal probability. The outcome was unusual. In hypothesis testing, where this leads is when we have unusual outcomes, we reject our initial assumption. And assume, or yeah, assume, we still don't know, and assume the alternate idea was correct, or alternate reason was true. So in this problem, the idea of hypothesis testing is the outcome was unusual, you think the game was rigged. It was not. So what would this tell us? This is we'll get to this later on. I just showed the coins were all tails. I'm gonna put them back up. No, I showed every coin had tails. Our assumption, or our conclusion that the game was rigged, was wrong. But without seeing the coin, you have no idea. And in the real world, in real world uses, you never see the coin. We just make a decision based on the unusualness of the event. But we can be wrong. And you know how you address that? If you can, and it's feasible, like flipping the coin more often, do more samples. Is an option. Let's look at how this plays. Let's just finish following up on our introduction here. So we had the idea that the coin was fair. We did a bunch of flips. It turned out getting 6 heads was unusual. And so we assumed that teacher had a rigged coin, and you were wrong. But you didn't know. You can only go off what you know. Now, usually it wouldn't be something like gambling or something like this, but let's give some examples of where this is. And what did we actually do during this process? What did we do? What did we do? This is the very heart of hypothesis testing. Very idea. Step 1 is we made an assumption about reality. Or truth of something. In this example, the coin was fair. Second, what did we do? We did some experimenting. We flipped the coin. We gather data to support or refute the claim. We we flip the coin 6 times. And then finally, we use probability and analysis to make a decision about our assumption. Or we inferred something about the reality, about the assumption. In our case, the coin was not fair. Okay? Which means you got made, you got had, you got punked by a huffy. You punked. I actually haven't even said what a hypothesis is, though. In statistics, in stats, a hypothesis is a statement about a characteristic of one or more populations. In this example, the population was a single coin or set of flips. And that characteristic is usually the parameters. So I'll pause and I'll let you write that down. Okay. So what kind of parameters did we have for the population? So known parameters that we use or that we've worked with so far. Remember, parameters apply to the population. And statistics apply to sample. And that's why we'd use the different symbols. Our parameters are well, we don't really change P. We use P for proportion. We tend to use P hat for a sample. We also have our mean, mu. So under the sample category, what was that? X bar. We looked at sigma, our standard deviation. That's S for a sample. And finally, we have sigma squared, is variance. We won't do a whole lot with variance, but it does show up. If you go further down the rabbit hole of statistics, it pops up. But variance is just standard deviation squared, the square of standard deviation. So those are our parameters, and those are our sample symbols. Let's look at an example of like the first three. There's the ones that are most commonly used. So here's our first one. Example A. I pulled this all from actual data This was actually my interview to be your teacher. I had to give a lecture on hypothesis testing, and so I presented these examples. And I got the job, so it works. These are good examples. Milk fat percentage. In California dairy milk. In 2012 was 3.72%. Researchers believe that a change in diet has changed this amount. So that's what we're talking about. What is our parameter here? The value they gave us was 3.72%. Percent often implies proportion. So the proportion of milk fat was 0.0372. And so what we do in hypothesis testing, our old claim was that the proportion is 0.0372. It says the researchers believe that a change in diet has changed this amount. Have they said that they think it is greater than it or less than it? Did they imply an increase or decrease? No, they actually didn't say. They just think it's different, which means we're going to say the probability is not equal to 0.0372. That's our first example. So keep that in mind. We're going to come back to these again. Category A was proportion, milk fat percentage. This was true. I pulled it from the ag reports. We do a lot of ag in Tulare and Visalia, and it seemed appropriate for our school. Other stuff we do in Tulare in agriculture, we have farming and stuff like that. So let's look at category B. Every increase by an inch in the standard deviation of plant-to-plant spacing of corn reduces corn grain yield by 2.2 bushels per acre. This has been explored experimentally. And so we have the World Ag Expo in Tulare. At the World Ag Expo, a new machine was introduced. Unveiled. And the creators claim that it reduces standard deviation over the previous best model which had a 4.5 standard deviation. Lot to take in. So what's our parameter here? Standard deviation, sigma. So our old claim was the previous settings. Sigma equaled 4.5 inches. The new claim, the manufacturer, the producer, the creator, claims it has reduced it. What does reduce mean mathematically? It means it's less than it. The standard deviation is less than 4.5 inches. Any questions? All right. Category C, final stats, final exam scores. Average 73%. We believe using computerized stats increases the average score. What's my parameter here? This is where the percentage symbol might throw you off. You see average or mean or something like that, we're looking at mean. So the old claim was that the mean equaled 73%. The new claim, or just 73, we'll say 73. The new claim, it increased it, it has gone up. The average is no longer 73. So those are the three examples we're going to explore right now. Okay. So I told you what a hypothesis test is. I even talked about hypothesis testing, but I haven't actually stated what a hypothesis test is. So a hypothesis test is a procedure that uses probability and sample evidence to choose between two competing hypotheses. And the plural of hypotheses has an ES, not an IS. The original claim or old claim goes by the notation H sub 0. We read this as, it sounds like H naught or H naught. The alternate claim or new claim goes by HA. Some books or some authors or papers, some books, papers, scientific studies use H1. So 0 versus 1 or original versus alternate. The H naught is called, it has a specific name, the null hypothesis. Okay. So I will use the phrase H naught. I will say null hypothesis. They are interchangeable. The null hypothesis is always, always, always a statement of equality. What does that mean? There's an equal sign. For a good test or a good experiment, one where the researcher set it up correctly, this is the old claim. And it should be. You don't want the old claim to be that it's greater than a specific amount. That's really vague. You want the old claim to be a specific amount. And the null hypothesis is the statement that is assumed to be true. And that's why it's usually, it's the old claim. The old claim is someone has done an experiment or sampled, there's reason to believe it's a specific amount. Usually it's by previous samples. Sometimes circumstances change. Like that milk fat problem, if the cows start eating something different, they change the diet, it might change the percentage of fat that's in dairy milk. Okay? So that's our null hypothesis, H naught, and it's the one assumed to be true. The alternate hypothesis, HA, this is the statement we are gathering evidence to support. It is a statement of inequality. Which means we're going to have a not equal sign, a less than, or a greater than. So we assume the null hypothesis be true. And we gather evidence to support the alternate one. Now, there's two ways this turns out. If the evidence or sample leads to an unusual occurrence, we reject the null hypothesis. And we support the alternate hypothesis. We support the claim being made. That's our first option. The other option is it was not unusual. And when that happens, we do not reject the null hypothesis, H0, and we do not support the claim. I think the easiest way to see the two outcomes is these ones both have do not in it. If it's not, and this is not. If it's not unusual, we don't reject the null hypothesis. We don't support the claim, the alternate hypothesis. Okay. So let's go back and look at the problems we gave and talk about what H0 and HA are. So the milk fat problem, or the milk fat hypothesis. The old claim said that P was 0.0372, and researchers assumed it to be different. Which is H0 and which is HA? H0 is the statement of equality. The top one has an equal sign. It's our null hypothesis. That makes this one our inequality, not equal. That's our alternate hypothesis. What about the corn problem? Corn yield. At the World Ag Expo, they said that they've decreased the standard deviation by 4.5 inches. It's less than 4.5 inches, and the old machine was 4.5 inches. Which is H0 here and HA? H0 is the statement of equality. In this problem, it's sigma equals 4.5. That makes the top one HA. Finally, stat scores. We had the mean was 73, and we as professors believe computerized stats increased it. Which is an H0 and HA here? The ho and the ha. Statement of equality is the top one here, equal sign. And this is the inequality. In hypothesis tests, it is custom to write H0 first. like I did in A and C. The only reason I did it different in B is because sometimes the problem isn't written in symbols like that, but they state the alternate hypothesis before actually stating the original one. You can't just go by what it is in order. The statement of equality is the null hypothesis. Okay, so I said we had two conclusions. One was to reject the null hypothesis, and one was do not reject it. When do we reject it? Let's be a little bit more specific. If H naught or the null hypothesis is true, it would be surprising based on the evidence. Which means there's enough evidence or sufficient evidence to reject H naught. In the problem we did, the very one we started with, the coins, our initial problem or our initial scenario was the coin flips. What was H naught and HA there? We assumed the probability of getting a heads was 0.5. After seeing a bunch of heads, our alternate hypothesis was that it's greater than 0.5. Okay. In a court, most of us have seen law shows. And some have even sat on a jury. What's the null hypothesis in a court of law? In law, what is the assumed outcome? H naught, we always assume it's innocent until proven guilty. You know what's funny though? In the court of law, H naught is not guilty. And we'll discuss why it's not. This says it should say innocent. Why don't we say innocent? Why don't we say they're innocent or guilty? We say guilty or not guilty. Those are the outcomes in a jury. The jury claims guilty or not guilty. The reason why we never declare a suspect innocent because we never know all the facts. unless the entire jury sat there and watched the whole event unfold, which would make them unqualified to be a jury because they were witnesses, we never declare a suspect innocent because we never know all of the facts. So we can just gather and we just say not guilty when there's enough evidence to support it. So I digress. I veered away. We were talking about rejecting the null hypothesis. Let's get back to that. Back to rejecting H0. So when we reject H0, if there's not enough evidence to support it, we reject it. In the court of law version, this is like finding the defendant guilty. So the court of law one, as we said, H0 was not guilty, which means what's the alternate claim here? They are guilty. Our conclusion or statement is always about or in regards to the alternate hypothesis, HA. And what would I say here? Back to the coin problem. There is sufficient evidence to support the claim that the coin was unfair in favor of heads. In general, when we do it, for any given problem, there is sufficient evidence to support the claim, or enough, you could say enough, to support the claim that, and then paraphrase the alternate hypothesis here. Put it in words. I didn't say probability was greater than 0.5. I said the coin was unfair in favor of heads. I put it in English. Most people don't talk in math jargon, and that's not what hypothesis testing is for. math and statistics is a tool. And when it's used, it's most often used in fields that are not necessarily super mathematical. Okay, it's more on like social sciences do a lot of studies and they do these statistics and stuff like that. Okay, that was our first option, rejecting the null hypothesis. Let's take a look at our other option. Our other option was we do not reject the null hypothesis. You will often see me write DNR, H naught. DNR. And what happens when this is the event? If H naught is true, it is not surprising based on the evidence. This is the idea of being found not guilty. If we had flipped equal coins and heads, we would not be surprised because coins are supposed to be fair. Okay. And our conclusion statement is always about the alternate hypothesis. If we do not reject H naught, we do not support HA. And I'll often say DNS HA. It gets easier. There is insufficient evidence. To support the claim that, again, paraphrase H naught here, or HA here. Put it in English. Put it in words. If you're writing in Spanish, put it in Spanish. French, French. Now, those are the two different options we have. There's a little more to this topic. Remember, our coin flip example, our conclusion was that there was sufficient evidence to support that the coin was rigged. We showed it to be false, though. This was an erroneous outcome. Okay, there's two ways we can error here. Two ways to error. So erroneous outcomes, what are our options? A type 1 error is alpha. We reject H0 even though it's true. In our court of law one, if we reject H0, we are rejecting that they're not guilty, which means we're supporting that they are guilty. And if it was wrong, it means we convicted an innocent person. This is the error we try to avoid the most. We'd rather let a thief keep on stealing they'll be caught again. And eventually they'll get evidence for it. We'd rather let a thief keep on stealing than steal someone's life away. Going to jail or prison has consequences long after jail or prison. Has consequences on one's life long after prison, and we don't want that. This is bad juju. We don't want that. How does this relate to what we did in the last section, confidence intervals? This is related to our confidence intervals in a huge way. The confidence interval percentage tends to be 1 minus alpha times 100%. Unless stated otherwise, we assume alpha equals 0.05 and confidence intervals 1 minus 0.05 times 100%. This leads us to a 95% confidence interval. Okay. The other type of error goes by beta. It's our Greek B, beta. That's where we fail to reject H0 even though we should. In the court of law, this is letting the guilty walk free. Now, court of law is very much tends to be not mathematical. If someone's up for being convicted or being tried to be a serial killer, people really want to make sure he's innocent. They're much more like they require more evidence of innocence or not guilty to back it, because people tend to be afraid of serial killers. They do not want someone that's going to kill a bunch more people. They tend to lower their confidence interval. They're going to be they require less to convict the person. That's the one we try to avoid. Let's take a look at our hypothesis test. This leads us into 10.2. So I'll start a new page for this. .2 is on our hypothesis test. And has 5 easy steps. Step 1, identify the 2 claims. And label H0 and HA. Two and 3 tend to go in different orders. It doesn't really matter. 3 is, I'll just do it the way I had before. 2 is find the test statistic. And StatCrunch will spit this out. We also want the p-value. And I'll go into that in a little bit. Why do we want this? We put this in research papers, so someone that goes over our work with our data set can reconstruct our results. Okay. Step 3, identify the level of significance. You will see this a lot. That is a phrase, the level of significance. And compared to our different outcomes earlier, this is alpha. If it is not given, assume alpha equals 0.05. Step 4. Compare the p-value with alpha. There's 2 possible scenarios. If the p-value is less than alpha, we reject H0. If the p-value is greater than alpha, we do not reject H0. Pause. That's step 4. And I'm going to put it in a way you can easily remember. Okay? Easy to remember. If the p-val is too low, reject the hoe. Low and hoe rhyme. If the p-val is too low, reject the hoe. We don't call it the hoe, we call it H0, but it works here. Like ho, 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 Santa Claus. Reject the hoe. You can take with it what you want. We also, if p-value is greater than or equal to alpha, I should say, we don't reject H0. And step 5, we state our conclusion. There is sufficient or insufficient evidence to support the claim, or yeah. And again, paraphrase HA here. The sufficient one arises when p-val is less than alpha. And this one is when p-val is greater than alpha. So 5 steps. The thing I think you're going to like the most, we will learn 8 different tests. The only step that ever changes is the first one. H0 and HA are different for each test. And steps 2 and 3 are given in the problem. Steps 2 by StatCrunch and 3 are given in the problem. Four and 5 are decision making and statements. Okay. So let's look at some examples of hypothesis tests. Let's do some. I'm going to need StatCrunch open, so maybe I should get that up and going. First example. Did it not open? It is believed that 50% of people are in favor of banning any cell phone usage while driving. A researcher believes this is too low. He believes it's too low. A researcher believes the actual value is higher. After surveying 1,000 people, he finds 534 are in favor of banning cell phone usage while driving. Test his claim at a 0.05 level of significance. Okay, that's our problem. Now, all of these hypothesis tests, we have to be able to use a normal calculator, have a normal distribution. For hypothesis testing. So, well, first off, we have to figure out what parameter they're looking at. That's going to tell us something big. What parameter are they looking at? Let's read the problem. Is believed, that should say that. Is believed that 50% of people are in favor of banning any cell phone usage while driving. That's a proportion. P equals 0.05. I'm sorry. P equals 0.5. Way to go, Jones. What does the researcher think? The researcher thinks it's higher. He thinks it's greater than 0.5. So we need to test this. That's what we're testing. Can we use a normal calculator first, though? Does this follow a normal? It either has to tell us it does, or we needed two things. Remember when we had proportions? We needed mu of p hat to equal p. Sigma p hat was p times 1 minus p over n. And we wanted n times p times 1 minus p to be greater than or equal to 10. And n had to be less than 5% of the population. Well, if he only surveyed 1,000 people, let's assume he's talking about America. That's where I live. You can't tell by my accent. So it's definitely less than 5% of the population. Maybe not when COVID-19 is done. That was a poor joke, sorry. 1,000 is much less than 5% of the population. That one's met. Let's check this one. We have 1,000 times 0.5 times 1 minus 0.5. If you work out that calculation, that's 250. That's definitely greater than or equal to 10. So this follows a normal distribution. Because n times p times 1 minus p was greater than or equal to 10. And it's safe to assume that 1,000 is less than 5% of the population. This means we can do our hypothesis test. So I'm going to pause here. You might want to hit pause. Okay. So let's look at our test. Step 1, identify H0 and HA. We said H0 was the statement of equality. The proportion is 0.5. HA was that probability was greater than 0.5. Step 2, find the test statistic. The way we do this in StatCrunch, stats, proportion stats, one sample with summary. Why is it with summary? He didn't give us the 1,000 names and find out who said yes and who said no. He just summarized the data and said 534 said yes. And when we do this, we want the hypothesis section. Let's take a look at what that wants here. It wants our number of successes. X is the number of successes. In this case, he's trying to see who's in favor of banning. So in favor of banning, and he gave us X was 534. N was our number of observations or sample size. He surveyed 1,000 people. Now in chapter 9, we clicked on hypothesis or confidence interval. Here we're going to do hypothesis test. The only things you can change are the proportion. It defaults to the value we need. Always, always, always check you have the right inequality sig. Check that you have the correct inequality symbol in the alternate hypothesis. We have HA is probability is greater than 0.5. That's what I'm going to put here. That's all I need. Successes, observations, the proportion, and what HA is. Compute. The test statistic was Z-stat. It shows Z-stat is 2.1503488. If you're putting in a research paper, there's no need to really round unless you feel like you need to. We could round that to 2.15. We also need to have the p-value. P-value, it tells us, is 0.0158. They are on the right side over here. You see that standard error? Guess what that is? Well, it tells us 0.015811388. In a second, I'm going to show you that that's the standard deviation. Okay? So that was step 2. Step 3 was identify alpha. Level of significance, it's given as alpha equals 0.05. Step 4, compare p-value and alpha. Our p-value is 0.0158. How does that compare to 0.05? (0.0158) is less than 0.005. 0.05. The p-val is too low, we reject the hoe. Okay. What's step 5? Step 5 is our conclusion. So we said the p-val is too low, we're going to reject the hoe. If we reject H naught, what do we do in terms of HA? We support HA. If p-value was not too low, we do not reject H naught, and we do not support HA. So here we're going to support HA. What was HA? HA was what the researcher believed. The proportion was higher than 50%. We had it up here also. P is greater than 0.5. So we're going to support HA. Get my camera set up the way I want it again. And remember that was P is greater than 0.5. So what am I going to say? There is sufficient evidence to support the researcher's claim that the proportion of people I'm paraphrasing what the problem was about. That want to ban cell phone usage while driving is greater than 50%. That's our statement. What do they do with this in reality? In reality, they will go on. In reality, they tend to go further and try to determine what it is. What proportion should be. Now, I told you we need to be able to use a normal calculator. Let's look at this from the normal calculator approach. So we had mu of p hat was equal to p, which is 0.5. Sigma of p hat was the square root of p times 1 minus p over n. 0.5 times 1 minus 0.5 over 1,000, take the square root, 0.015811388. Our p hat, our actual p hat, is x over n, 534 over 1,000, which is 0.534. What we're trying to do is show is p hat more than 2 standard deviations away. From the given p. That would make it unusual. And we would reject the null hypothesis. Okay. Let's just take a look at what that looks like on a normal bell curve. I'm going to use 0.0158 or 0.016. Let's just go to 3 decimal places. Let's look at our normal bell curve. The p that goes in the middle was the given p. 1 standard deviation out, mu plus sigma. This is 0.516. Mu plus 2 sigma is 0.532. Mu minus sigma, and I'm using my mu and my sigma right here. Those are the values I'm using. This is where I'm getting these numbers. 0.484, and minus 2 sigma is 0.468. The idea here is if we land in this region, if we find p hat in this region, that's our 95% confidence interval range. It is not unusual. Where did p hat go though? P hat was 0.534. Notice it's also given in StatCrunch. Is in StatCrunch in the test under sample prop. So here, p hat is outside the 95% confidence interval. And thus we reject H naught. And the idea behind that is we assumed p equals 0.5, the initial given values. Is true. Getting p hat of 0.534 appears to be unlikely if that assumption is true. Or unusual if that assumption is true. So we reject it. Thus, p is probably not 0.5. And our test showed not only is it not 0.5, but it's higher than 0.5 because it's on the right side over here. Higher than 0.5 by more than 2 deviations. Let's show you it in the normal calculator. I don't want to lose this window. We're going to keep it. Stats, calculators, normal. I'm going to put our mean and standard deviation back up so we can see it. The mean was 0.5. The standard deviation was 0.015811388. And we're looking at the probability that X is greater than 0.534. So in the normal calculator, enter mean as 0.5. Sigma we calculated 0.015811388. And we're looking at the probability that X is more extreme than what we had. You click compute. And to 4 decimal places, what does that give us? 0.0158. So normal calculated result. Where else did we see 0.0158? Our p-value, see that? That's the p-value from the hypothesis test. So the whole doing that's the stats, proportion stats, one sample with summary, doing this thing here, it's really just designed to speed up the whole process. You don't need to enter the stuff in the normal calculator, calculate p-hat, it just spits it all out for you all at once. Let's do that same thing and let's look at the confidence interval. From a confidence interval perspective, again, stats, proportion stats, one sample with summary. This time use the the confidence interval box. It gives us a lower limit, 0.503, and an upper limit of 0.565. This is from StatCrunch. P equals 0.5 is outside the 95% confidence interval. That's another way of looking at why we're rejecting it. It's too unlikely given our confidence interval. So these all kind of tie together. The normal calculator we've used, the confidence interval, these hypothesis tests, they're all related. Okay. So that was 10.2. So that wraps up 10.2. Which is on hypothesis test. Where the parameter is P. And we have one sample. Okay. I do want to take a look at, let's change this problem just a little bit. I want to explore a little bit more. Let's change the hypothesis, change the alternate hypothesis to P does not equal 0.5. He didn't say higher or lower. This is going to change some stuff. And the reason why is when we went, this affects things. CI we use actually. When we had P greater than 0.5, we had P here, we had P plus 2 sigma, and we were trying to see if P hat was greater than P plus 2 sigma. If we do P is less than 0.5, and let me finish the idea here. Actually, I want to explore this a little bit more later. I don't think you guys are ready for this part yet. Let's come back to this. Work with this for a little bit. Get the hypothesis tense down. Lock down the steps of the hypothesis, and then we'll start looking at comparing it to HI. Okay. Let's call that a wrap. Peace.